Hi, this is the element distinctness problem. I'm Mauricio Atamura. This is for COT 5405. So what is the element distinctness problem? We have an array of well not, well, all n elements in no particular order in an array, and we want to find out if each element is distinct. So that means if all elements in the array are unique, such that none of the numbers are repeated. Now, we want to use the model of computation, which is comparison based. So we can only compare two numbers at a time, say x and y, and we can do so in constant time. And then we can get an answer whether it's greater than, equal to, or less than. Now the problem can be easily solved in big O n log n time via sorting. So we would use something like, for an example, merge sort, and that takes big O n log n time to just sort the array, and then we could just go through the array once and see if the numbers one after another are equal to, and if they are, then the array is not unique. So we want to prove that omega n log n is the lower bound for this type of problem. So we have n numbers in an array, and we are given them in random order, so it's not sorted. So there's n factorial permutations of those n numbers. If we use a decision tree, we can see that all the leaves at the end of the tree, at the bottom of the tree, have to be n factorial. Thus, the height of the tree, which is h, is going to be greater than log of the height, which is log of n factorial, which is n log n. So using a decision tree, we could just put the array into the decision tree, and using greater than or equal to and or less than and equal to and greater than, we can have the leaf nodes be the permutations in based on like what order the array is in. So for an example, if we have three numbers in our array, 1, 2, and 3, there are 3 factorial permutations, which is 6, and each of those leaves are at the bottom of the tree, and they don't all have to be at the same level. For an example, the permutation of 1, 2, 3 means that from the roots we would go left and know that 1 is less than 2, and then we would go left again and know that 2 is less than 3. And since 2 is less than 3 and 1 is less than 2, 1 is less than 3, and we can put it in that order. This is what a 3 element decision tree would look like. So we can assume that we could use some number that's less than or equal to k comparisons to sort the array. And if we do so for n factorial inputs, we would need some number that's less than or equal to 2 to the power of k, since k is the number of comparisons that we need to sort, and we can only do 2 comparisons. We can only compare 2 numbers at a time. So n factorial has to be less than or equal to 2 to the power of k. and 2 factorial is greater than or equal to n over 2 to the power of n over 2, which we could use to just simplify the problem. And then 2 to the power of k, we can take the log of that side and take the log of the other side and get that k is greater than or equal to n over 2 log n over 2, which is more generally n log n. We could so we have our array of n numbers. We can assign them all as x1, x2, x3 until xn. Then we can also get a y array that is a permutation of x such that it's not the exact same permutation. It has to be a different permutation than what x already is. And then we can make that y1, y2, y3 until yn. Then we can make a equation called z and make it so that it looks similar to like a times x plus b times y, which is a linear line. So we can plug in a as a constant, a random number, and then plug in each value of xi and yi, and we know that we have to have it so that xi is less than xj and yi is less than yj. So this is completely possible because since y is a permutation of x such that y is not the exact same permutation of x, we know that at least one position of both of those arrays has to be different, as in x of I cannot be equal to x of j, and thus z of I has to be less than z of j. And thus, x and y must reach distinct yes leaves. So the leaves that result in yes, such that like the path using each permutation in the same graphical region is different. So each leaf that ends in a yes means that each leaf that ends in a yes means that all the elements are unique and are proven by following this path from the tree. And thus, the element distinctiveness problem can be solved in a lower bound of omega n log n. And these are some resources for further reference.